Alright guys, today's goal, the learner will understand modeling with functions. Okay? So, what you'll learn about functions from formulas, functions from graphs, functions from verbal descriptions, and functions from data. And why? Using a function to model a variable under observation in terms of another variable often allows one to make predictions. In particular situations, such as predicting the future growth of a business based on data. Okay? That's a huge one, guys. Future growth based on data. Alright. A square of side x inches is cut out of each corner of an 8-inch by 15-inch piece of cardboard. And the sides are folded up to form an open top box. Write the volume of a function x. B, find the domain of the volume as a function of x. And C, graph the function. Graph V as a function of x over the domain found in part B. And use the maximum finder on your grapher to determine the maximum value such a box can hold. How big should you cut, or how big should the cutout squares be in order to produce the maximum volume? Okay. Alright. So, let's see. Write the volume as a function of x. So, V of x. Well, we know it equals length times width times height. So, the length is going to be 15 minus 2x because they cut x off each corner. The width, 8 minus 2x. The height is x. Okay? So, V of x equals x times 15 minus 2x times 8 minus 2x. So there we go. There's the volume as a function of x. Let's see how we did. And that's what they have. Didn't even have to simplify it, so we can just keep moving on now. Okay. It says a square has a side of x inches. It's cut out of each corner. Well, you know that x has to be greater than 0. So, find the domain. What's the maximum it could be, though? Well, if you think about this, if the height is 4 and you cut 4 inches off each side, the domain has got to be from 0 to 4. I guess you could technically say greater than 0. It wouldn't have a volume, but still you could cut nothing off and you'd have a strip. So, but then the maximum also, it would eliminate all of the width because 4 times 2 is 8. 8 minus 8 is 0. So anywhere between 0 and 4. So there we go, anything between 0 and 4. So now we have to try to figure out how to graph this. Alright, so there we go, you get the 8 minus 4. So 0 to 4, so we were right. Alright, so let's take a look here. If we say V of 0, you're going to get 0. And remember, we're plugging into this. So if you have 0, 0, if you have 1, plug in 1, you get 1 times 13 times 6, 78 inches cubed, because it's a word problem here. Plug in 2, you get 2 times 11 times 4, 88 inches cubed. Plug in 3 times 9 times 2. So So it's already going back down. So it looks like the max is going to be somewhere around 88. So plug in 4, you're going to get 0 again. Alright, so let's take a look at this when we use our graphing calculator to find the maximum. So yeah, if you go through find the max, it looks like right there. So the maximum volume is 90.74 inches cubed. And that occurs when you took x to be 1 2/3 of an inch. Okay. So how big should the cutout squares be in order to produce the box of maximum value? Well, according to this, it's telling you right there. So 1 2/3 of an inch. Alright. Here's another example. Finding the model and solving. Grain is leaking through a hole in a storage bin at a constant rate of 5 cubic inches per minute. Notice it says cubic because we're dealing with volume. The grain forms a cone-shaped pile on the ground below as it grows. The height of the cone always remains equal to its radius. So right there, I would underline that. Circle. If the cone is 1 foot tall now, how tall would it be in 1 hour? Okay. So, here's the thing we got to think about. It told us, so we know that the height of the cone, so height equals radius. Volume of a cone, 1/3 pi r squared h. But we know h equals r, so that would be 1/3 pi r cubed. Okay. It says if the cone is 1 foot tall now, how tall will it be in 1 hour? Okay, well, let's see. Well, let's plug in what it is. Let's find out what the volume is right now. Now it says, notice how it says 5 cubic inches per minute. So how 1 foot is how much in an inch? 12. So you would say the volume equals 1/3 pi times 12 cubed. So let's see. This equals 576 pi. Well, it says grain and leak in a hole storage bin at a constant rate of 5 cubic inches per minute. Well, how many minutes are in an hour? So you can say it's going to grow 60 times 5, so 300 cubic inches. So add that to it. So we know the volume equals that. But we want to know the height. Well, don't we know volume equals 1/3 pi h cubed as well? Over, and that equals this. So if you solve that equation, multiply by 3, divide by pi, you can get h cubed equals 3 times 576 pi, I forgot the pi up there, plus 300 divided by pi. Take the cube root, and you would get the height is approximately 12.63 inches. Okay? Constructing a function from data. Given a set of data points of the form x comma y. To construct a formula that makes appropriate y as a function of x, make a scatter plot. The points do not need to pass the vertical line test, or the points, do not need to pass the vertical line test. Determine from the shape of the plot whether the point seems to follow the graph of a familiar type of function, a line, a parabola, a cubic, the sine curve, the 12 basic functions. Transform a basic function of that type to fit the points as closely as possible. So let's take a look. So here's some things. Functions. We're going to be doing linear and quadratics, cubics, quartics, all in chapter 2, and then there's the natural log. Okay? These are things we're going to be looking for. These are the ones you're going to have to match. Okay? And then there's exponential, power function, logistic, and sinusoidal. Okay? These are what we're going to be seeing. We'll go over an example of this tomorrow. See you guys then.